There's a photograph that changed everything. It was taken by Voyager 1 in 1990 from 3.7 billion miles away. In it, Earth appears as a tiny speck, barely visible against the vastness of space. When Carl Sagan saw it, he said something that still haunts us today. Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on a mote of dust suspended in a sunbeam. For decades, this became our defining narrative. We are insignificant, we are nowhere special, we are cosmic accidents clinging to a random rock in an indifferent universe. But here's what Carl Sagan didn't know in 1990. Here's what scientists discovered only in the last few years, using data from missions like Gaia and advanced galactic surveys. Here's what changes everything about that photograph. That random location, it might be the least random place in the entire Milky Way galaxy. And there's something deeply, profoundly unsettling about where we are. Let's start with what you were taught in school. The story goes something like this. Earth orbits an average star. The Sun is one of hundreds of billions of stars in the Milky Way. Our solar system sits in an unremarkable spiral arm, about 2/3 of the way from the galactic center. The Milky Way itself is just one galaxy among trillions in the observable universe. This is the Copernican principle, named after the astronomer who proved Earth isn't the center of the solar system. Over centuries, we extended this principle further and further. We're not at the center of the solar system. We're not at the center of the galaxy. We're not at the center of the universe. We're not special at all. This idea became almost sacred in astronomy. It's called the principle of mediocrity, the assumption that Earth occupies no privileged position in the cosmos, that we're cosmically average in every measurable way. Scientists love this principle because it made calculations easier. If Earth is typical, we can extrapolate from our observations. If life arose here, it probably arose in countless places. If we can see the universe clearly, other civilizations probably can too. For 100 years, this was bedrock. This was truth. This was scientific orthodoxy. But what if I told you that almost everything about that story is wrong? What if our unremarkable location is actually the most remarkable thing about us? What if the very characteristics that make us feel insignificant are the exact characteristics that make our existence possible? What if we're not cosmically average at all, but rather we're sitting in a location so improbable, so perfectly calibrated, so statistically anomalous that it demands explanation? December 2022. A paper published in the journal Nature sent shockwaves through the astronomical community. The European Space Agency's Gaia spacecraft had spent years mapping the positions and movements of over 1.8 billion stars in our galaxy with unprecedented precision. And when astronomers analysed this data, they found something extraordinary. Our Sun, our solar system, our entire cosmic neighbourhood sits inside what's called the local bubble, a cavity in space approximately 1,000 light-years across. This isn't empty space. It's a region of extremely hot, extremely low-density gas, surrounded by a shell of much denser, cooler material. You might think, okay, so we're in a bubble. So what? Here's the so what. This bubble was carved out by a series of catastrophic supernova explosions. According to the research by Catherine Zucker and her team at the Harvard-Smithsonian Center for Astrophysics, at least 15 massive stars exploded over the course of several million years, with the burst of activity peaking roughly 14 million years ago. The shockwaves from these explosions blasted away surrounding gas and dust, creating this enormous cavity. And here's what makes our position remarkable. We're not floating randomly inside this bubble. We're positioned near the edge, in the shell where the compressed gas is now triggering new star formation. Let me put this in perspective. The Milky Way galaxy is approximately 100,000 light-years across. The local bubble is 1,000 light-years across. That means the bubble occupies roughly 1/1,000,000th of the galaxy's volume. What are the odds that our solar system just happens to be located right at the edge of this structure at this particular moment in its evolution? Rough statistical estimates suggest this positioning is approximately a 1 in 10,000 occurrence, though the exact probability depends on various assumptions about stellar distributions and timing. Now, a skeptic might say, well, someone had to be in that rare position, why not us? Fair point. Let's table that for now. But here's where things get strange. The local bubble isn't the only improbable thing about our location. It's not even in the top 5. We're going on a journey. We're going to zoom out from Earth, layer by layer, examining our position in the solar system, the galaxy, and the cosmos. And at each layer, we're going to find the same pattern. We're not where random chance alone would predict we should be. Before we begin, let me establish the structure of this journey. We're going to move outward in concentric shells. Layer 1, Earth's position in the solar system. We'll examine the statistical anomalies of our planet's orbit, the Moon's formation, and Jupiter's protective role. Layer 2, the solar system's position in the Orion Spur. We'll explore why our location between the major spiral arms might be the most critical factor for life. Layer 3, our position in the galactic habitable zone. We'll investigate how the Milky Way's violent history of galactic cannibalism set the stage for our existence. Layer 4, the temporal dimension. We'll uncover why, when we exist, might be just as improbable as where we exist. Layer 5, the philosophical crisis. We'll confront what these patterns mean for our understanding of reality itself. At each layer, I'm going to present you with data, hard numbers, peer-reviewed research. Then I'm going to show you the patterns that emerge when you step back and look at the big picture. Some of these patterns will make you uncomfortable. They made me uncomfortable when I first encountered them, because they challenge the Copernican principle at its core. But here's the thing about science. It doesn't care about our comfort. It doesn't care about philosophical preferences. It cares about data. And the data is telling us something extraordinary. So buckle up, strap in, because this journey doesn't just reveal our place among the stars. It reveals that our place among the stars might be the greatest mystery in all of science. Let's begin. Let's start close to home, with Earth itself. You've heard about the Goldilocks zone, that narrow band around a star where liquid water can exist on a planet's surface. Not too hot, not too cold, just right. Earth sits comfortably in the Sun's habitable zone, about 93 million miles away, 1 astronomical unit. But here's what most people don't realize. The habitable zone isn't a guarantee of habitability. Venus is arguably within the inner edge of the Sun's habitable zone, so is Mars at the outer edge. Venus is a hellscape with surface temperatures hot enough to melt lead. Mars is a frozen desert with an atmosphere 1% as thick as Earth's. What makes Earth different isn't just the distance, it's a cascade of perfect positioning. First, Earth's orbit is nearly circular. The eccentricity, the measure of how elliptical an orbit is, stands at 0.0167. 0 would be a perfect circle. Most exoplanets we've discovered have eccentricities above 0.2. Many exceed 0.5, meaning they swing wildly between scorching summers and frozen winters as their distance from their star changes dramatically. Earth's near-circular orbit means our seasons are caused by axial tilt, not Hawk distance variation. This creates stable, predictable climate patterns, the same patterns that allowed agriculture to develop, the same patterns that allowed civilizations to plan, to build, to accumulate knowledge across generations. When astronomers analysed the Kepler Space Telescope data, over 2,600 confirmed exoplanets, they found that among well-characterised systems, fewer than 20% have orbital eccentricities as low as Earth's. Already, we're in a relatively rare category just by this one metric, though detection biases may affect these numbers. But let's zoom out to the solar system scale. Jupiter, the gas giant sitting 5.2 astronomical units from the Sun. For decades, we thought of Jupiter as just another planet. Then we started discovering exoplanetary systems, and we realized Jupiter is weird. Most gas giants we've found are hot Jupiters, massive planets orbiting incredibly close to their stars, often closer than Mercury is to our Sun. These hot Jupiters likely form farther out, then spiral inward through orbital migration, potentially destroying any rocky planets in their path. They're system wreckers. Jupiter didn't do that. It formed far out and stayed far out. And because it stayed far out, its massive gravity acts as a cosmic shield. Comets and asteroids that might otherwise bombard the inner solar system can be captured by Jupiter or flung out of the system entirely. The evidence? Look at Jupiter's moon Europa. Its surface is covered in impact craters. Look at Earth's moon. Far fewer craters, especially recent ones. Jupiter appears to be intercepting some impacts. Now, the role of Jupiter is debated. Some simulations suggest Jupiter significantly reduces impact rates on Earth, potentially by orders of magnitude. Other studies, like work by Horner and Jones, show the picture is more complex. Jupiter's influence depends on its exact orbital configuration and can sometimes increase impact rates. The consensus is that Jupiter provides net protection, but the exact factor remains uncertain. Time for multicellular organisms to evolve, time for intelligence to develop, time for civilizations to form. Jupiter likely gives us that time. But here's the kicker. Jupiter's current orbit is stable. Many gas giants in other systems have chaotic or migrating orbits, changing over time due to interactions with other planets. Jupiter's orbit has remained essentially unchanged for billions of years. The gravitational resonances with Saturn lock both planets into stable configurations. The odds of a planetary system having a near-circular rocky planet in the habitable zone, approximately 10 to 20%, a gas giant in the outer system in a protective configuration, approximately 10 to 15%, that gas giant in a stable, unchanging orbit, approximately 30%. If we conservatively estimate combined probability, approximately 0.3% to 0.6%, or roughly 1 in 200 to 1 in 330 planetary systems. And we haven't even talked about the Moon yet. Earth's moon is absurdly large relative to its planet. The moon is 27% the diameter of Earth. For comparison, Mars's largest moon, Phobos, is 0.0004% the diameter of Mars. Jupiter's largest moon, Ganymede, is 3.7% of Jupiter's diameter. Earth's moon is proportionally massive, and here's why that matters. The moon stabilizes Earth's axial tilt. Right now, Earth tilts at 23.5 degrees. This tilt gives us seasons. Without the moon's gravitational influence, Earth's tilt would vary wildly over time, from 0 degrees to 85 degrees, due to gravitational perturbations from Jupiter and Saturn. Mars doesn't have a large moon. Its axial tilt has varied between 13 degrees and 40 degrees over millions of years. When Mars tilts to extreme angles, its poles point more directly at the Sun during summer, causing dramatic climate swings. Earth's stable tilt means stable climates over millions of years. Evolution doesn't get constantly reset by catastrophic climate chaos. But there's more. The Moon creates tides. Tides create tidal pools. In 2016, research by Ralph Pudritz at McMaster University suggested that tidal pools, with their rhythmic wet-dry cycles, might be among the ideal environments for the chemical reactions that sparked life. The concentration of organic molecules, the energy input from evaporation and rehydration, the protection from the open ocean. Without the Moon, Earth would still have tides from the Sun, but they'd be about 1/3 as strong. The tidal pool hypothesis becomes much less viable. How did Earth get such a massive moon? The leading theory, a Mars-sized protoplanet called Theia, collided with the early Earth approximately 4.5 billion years ago. The impact was calibrated within a narrow range, energetic enough to eject material, but not so violent that it shattered Earth completely. The debris from the collision coalesced into the Moon. The probability of such a collision with such precise parameters. Current estimates suggest fewer than 10% of rocky planets experience giant impacts that create large, stable moons in habitable configurations. We're now in a relatively rare category just from our local positioning in the solar system, and we haven't even left our cosmic neighborhood yet. Now let's zoom out. Let's look at where the entire solar system sits within the Milky Way galaxy. The Milky Way is a barred spiral galaxy, approximately 100,000 light-years in diameter. Recent estimates suggest it contains between 100 and 200 billion stars, with newer surveys favoring the lower end of this range. It has a supermassive black hole at its center, Sagittarius A star, with a mass of approximately 4 million solar masses. Our Sun sits roughly 26,000 to 27,000 light-years from the galactic center. That puts us about 2/3 of the way out from the center to the edge. This position defines what astrobiologists call the galactic habitable zone. Too close to the galactic center, and you have problems. Problem 1. Radiation. The galactic center is a high-energy environment. You've got the supermassive black hole accreting matter and spewing out X-rays. You've got a dense concentration of stars, meaning more frequent supernovae. You've got cosmic rays permeating the region. Any planets there would be exposed to elevated radiation levels. Problem 2. Gravitational chaos. Near the galactic center, stars are packed densely. The average distance between stars is about 0.4 light-years, compared to roughly 4 light-years in our neighborhood. Close stellar encounters become more common. A passing star could gravitationally disrupt a planetary system, destabilizing planet orbits or sending comets cascading into the inner system. Problem 3. Metallicity balance. Wait, isn't more metal a good thing? Near the galactic center, there's substantial heavy element enrichment from countless generations of supernovae. While this provides planet-building materials, extreme metallicity might create other challenges. The just right metallicity is critical, but you can't go too far from the center either. Problem 4. Insufficient metals. In the outer reaches of the galaxy, beyond about 50,000 light-years, there hasn't been enough stellar recycling. Stars form from gas that hasn't been enriched by as many previous generations. Heavy elements don't concentrate as much, making Earth-like rocky planets less likely. You get more gas giants and ice worlds. The galactic habitable zone, where metallicity is balanced, radiation is manageable, and stellar encounters are rare, forms a ring roughly between 20,000 and 30,000 light-years from the galactic center. Our Sun, at approximately 26,000 light-years, sits right in this favorable zone. Okay, you might say, but the ring is 10,000 light-years wide. Surely lots of stars are in this zone. Yes, approximately 20% of the galaxy's stars sit in this optimal ring, so we're in the top 20%. Not terrible odds, but we're not done yet. Because it's not just where you are in the galaxy, it's how you move through the galaxy. Our solar system orbits the galactic center once every 225 to 250 million years. This is called a galactic year, but here's the critical detail. Our orbit is nearly circular. The Sun's orbital eccentricity around the galaxy is approximately 0.05. Just like Earth's orbit around the Sun, this is relatively circular for a galactic orbit. Why does this matter? Because the Milky Way has spiral arms. These aren't rigid physical structures like the arms of a pinwheel. They're density waves, regions where stars, gas and dust temporarily bunch up due to gravitational interactions. As matter moves through these density waves, it gets compressed, triggering bursts of star formation. Star formation means supernovae, lots of them. Spiral arms are more violent, radiation-elevated environments. Most stars in the galaxy have eccentric orbits that cause them to periodically cross through the spiral arms. When they do, they're exposed to increased radiation, gravitational perturbations, and potentially increased comet impacts as objects in their Oort clouds get disturbed. Our solar system largely avoids this. Our relatively circular orbit keeps us in the calmer space between two major spiral arms, the Sagittarius arm and the Perseus arm. We're in what's called the Orion Spur, a minor structure we'll discuss in detail shortly. But the key point: we don't regularly cross major spiral arms. We stay in a relatively quiet zone. Research by astronomer Guillermo Gonzalez has analysed stellar orbital dynamics in the context of habitability. Studies suggest that a minority of stars in the galactic habitable zone, perhaps 5 to 10%, have orbits circular enough to largely avoid major spiral arm crossings. Let's update our calculation using conservative estimates. We begin with a base assumption. 1 in 3,000 planetary systems may have the right conditions for habitability. Next, we adjust for location, multiply by 5, since only about 20% of systems lie within the galactic habitable zone. Then we account for orbital stability, multiply by 15, because only around 5 to 10% of systems have sufficiently circular orbits. Putting it all together, 1 in 3,000 times 5 times 15 equals approximately 1 in 225,000. That's our conservative estimate for how many planetary systems might meet all the criteria for long-term habitability. We're now in a relatively rare category of stars in the galaxy, just from position and orbital dynamics. But the strangeness doesn't stop there, not even close, because now we need to talk about the local bubble in detail. Remember that paper I mentioned at the beginning? The December 2022 publication in Nature by Catherine Zucker and her team at the Harvard-Smithsonian Center for Astrophysics? Let me give you the full story, because this is where things start to feel less like science and more like science fiction. Approximately 14 million years ago, recent in cosmic terms, a region of space near the Sun experienced a catastrophic chain reaction. One massive star went supernova. Its shockwave compressed nearby gas clouds, potentially triggering the formation of more massive stars. These stars lived fast, died young, and exploded as supernovae themselves. Over the course of several million years, at least 15 supernovae detonated in the same region, with the main burst of activity occurring roughly 40 million years ago. Each explosion released tremendous energy. The combined blast carved out a cavity in the interstellar medium, the local bubble, now spanning approximately 1,000 light-years across. Over the course of several million years, at least 15 supernovae detonated in the same region, with the main burst of activity occurring roughly 40 million years ago. Each explosion released tremendous energy. The combined blasts carved out a cavity in the interstellar medium, the local bubble, now spanning approximately 1,000 light-years across. The shockwave swept away gas and dust, compressing it into a dense shell at the bubble's edge. This shell became gravitationally unstable and started collapsing under its own weight, forming new stars. Today, when we map nearby young stars, stars less than 20 million years old, we find something astonishing. They're nearly all located on the surface of the local bubble. Every major star-forming region within 500 light-years of Earth, Taurus, Perseus, Ophiuchus, Lupus, sits on or near the bubble's shell. We're watching, in real time, a new generation of stars being born from the remnants of the previous generation's death. And we're sitting right near the edge, well positioned to observe it. But here's where the timing becomes noteworthy. The supernova burst peaked roughly 14 million years ago. The bubble has been expanding ever since at approximately 6 kilometers per second. It's now about 1,000 light-years wide and still growing. Our solar system is 4.6 billion years old. For most of its existence, it was not in the local bubble. We were somewhere else in the galaxy, following our orbit. We entered the local bubble approximately 5 to 10 million years ago, according to the Zucker team's analysis. Think about that timeline. The supernovae peaked roughly 14 million years ago. We entered the bubble 5 to 10 million years ago. That means we arrived after the most intense radiation had dissipated, but while the bubble is still active and expanding. If we'd been present during the supernova burst itself, Earth would have faced intense radiation exposure. While not necessarily sterilizing at this distance, it could have caused significant atmospheric and biological stress. If we arrived 50 million years from now, we'd enter a bubble that's expanded and merged with surrounding structures, no longer distinct. The current dynamic star-forming environment would be over. We arrived in a relatively favourable window after the most intense danger, during peak observational interest. The Zucker team's analysis suggests that the timing and positioning of our entry into the local bubble represents a relatively uncommon occurrence, though exact probabilities depend on assumptions about stellar motions and bubble evolution. But it gets more interesting. Remember, I said we're near the edge of the bubble, not floating randomly in the interior. The bubble is 1,000 light-years across. If we were randomly positioned inside it, we'd most likely be somewhere in the interior, hundreds of light-years from the shell. But we're not. We're within roughly 50 light-years of the shell where active star formation is occurring. The shell itself is roughly 100 light-years thick. The probability of being within this observationally privileged zone, given that you're inside the bubble at all, is considerably lower than being randomly positioned anywhere within the bubble's volume. Let's update our master calculation using conservative estimates. We begin with a base figure. 1 in 225,000 stars may have the right stellar position and orbital stability. Next, we adjust for timing and location within the local bubble. Multiply by 20 to 30 to reflect how rare it is for a star to be in the right place at the right time within this small region of space. Putting it all together, 1 in 225,000 times 20 to 30 gives us a final estimate of approximately 1 in 5 to 7 million stars. We're now in an increasingly rare category, and here's what makes this particularly interesting. We're not done finding improbable factors, we're just getting started. Because the local bubble isn't just a passive cavity, it's having active effects on our environment. Research published in 2023 by Merav Ofer at Boston University suggests that the local bubble may be providing some shielding from cosmic rays. The hot magnetized plasma in the bubble's structure could deflect some of the high-energy particles that would otherwise reach our solar system. The magnitude of this effect is still being studied, but it represents another way our local environment may be favorable for life. The bubble is both protecting us and giving us a front row seat to star formation. Coincidence? Maybe. Let's table that thought. But before we move to the next layer, I want you to consider something. Every factor we've discussed, Earth's orbit, Jupiter's configuration, the Moon's formation, our galactic orbit, the local bubble timing, these are largely independent variables. They don't directly cause each other. Earth's circular orbit doesn't create the local bubble. The Moon's formation doesn't determine our galactic position, and yet all of them align favorably for complex life. In statistics, when independent variables all point in the same direction, we call that a pattern, and patterns demand explanation. So let's keep going. Let's zoom out to the next layer, the Orion Spur, the intriguing galactic structure we call home. Here's something that will surprise you. For most of human history, we had no idea what the Milky Way even looked like. Think about it. We're inside the galaxy. Trying to map the Milky Way from Earth is like trying to draw a map of a forest while standing in the middle of it. You can see trees around you, but the overall structure, nearly impossible. It wasn't until the 1950s that astronomers, using radio telescopes to peer through the dust, started mapping the spiral arms. They identified 4 major arms: Scutum Centaurus, Sagittarius, Perseus, and Norma. These are the grand structures of our galaxy, regions where star density increases, where gas compresses, where the spectacle of star birth and death plays out. And between the Sagittarius and Perseus arms, they found us. For decades, astronomers assumed we were in some kind of minor connecting structure, a bridge of stars between the major arms, nothing special. They called it the Orion Spur, or sometimes the Orion Arm, but that second name always felt aspirational. It wasn't a real arm, it was just stuff between the real arms. Then, in 2013, something changed. A team of astronomers led by Alberto Sanna at the Max Planck Institute used very long baseline array radio telescopes to measure the distances to massive star-forming regions with unprecedented precision. They were trying to map the Perseus arm more accurately. What they found shocked them. The Orion Spur isn't a minor structure at all. It's approximately 20,000 light-years long. It has its own distinct structure, its own star formation dynamics, its own gravitational identity. It's not connecting the major arms. It's running parallel to them, offset by about 6,500 light-years. In Alberto Sanna's words, "We were terribly wrong about the local structure of the Milky Way. The Orion Spur is substantial enough that some astronomers now argue it should be reclassified as a full spiral arm in its own right. Not one of the 4 major arms, but a significant 5th arm. Why does this matter? Because if we were in a major spiral arm, we'd be in a cosmic shooting gallery. Major spiral arms are where the galaxy's density waves compress gas most efficiently. Star formation rates are estimated to be 3 to 5 times higher in major arms than in inter-arm regions. And where you have high star formation, you have short-lived massive stars. And where you have massive stars, you have supernovae. A 2019 study by Diederik Cruyssen at the University of Heidelberg calculated supernova rates in major spiral arms. approximately one supernova every 30,000 to 50,000 years within a 1,000 light-year radius. That might not sound like much, but consider, a supernova within 30 light-years would strip Earth's ozone layer and likely cause mass extinction. A supernova within 100 light-years would significantly increase radiation levels, potentially affecting mutation rates. A supernova within 300 light-years could influence climate patterns through increased cosmic ray flux. Over the timescales required for complex life to evolve, hundreds of millions to billions of years, being in a major spiral arm means repeated exposure to these events. Evolution faces constant challenges. Complex multicellular life struggles to maintain stability. But in the Orion Spur, the supernova rate appears to be approximately 1 every 100,000 to 200,000 years within a 1,000 light-year radius. That's roughly 2 to 4 times less frequent than in the major arms. The difference between an environment where complex life faces frequent disruptions and an environment where complex life has time to develop complexity. Now, you might ask, if the Orion Spur is so substantial, why does it have lower star formation than major arms? Excellent question. And the answer reveals yet another just right factor. The Orion Spur has enough star formation to enrich the local environment with heavy elements. Remember, we need supernova-forged elements like iron, silicon, carbon, oxygen to build rocky planets and organic chemistry. But not so much star formation that we're constantly exposed to elevated radiation. It's a Goldilocks spur, active enough to be chemically rich, calm enough to be biologically favourable, and remember our relatively circular galactic orbit. That orbit keeps us in the Orion Spur. We don't drift into the more dangerous major arms. We stay in this stable, intermediate structure. When Guillermo Gonzalez analysed the galactic distribution of potentially habitable planetary systems, he found that minor spiral structures, spurs and inter-arm regions appear to be the most favourable locations. Major spiral arms present significant challenges. But here's the twist. Substantial minor spurs like Orion are relatively rare. Most spiral galaxies have 2 to 4 major arms and limited minor structure. The Milky Way's particular morphology, with a prominent spur running parallel to major arms, is present in an estimated 10 to 15% of similar spiral galaxies. Another filter, another source of rarity. But there's something else about the Orion Spur that rarely gets discussed. Something that makes our situation even more unusual: the view. In 2004, astronomer Guillermo Gonzalez and philosopher Jay Richards published a controversial book called The Privileged Planet. The central thesis was provocative. The same rare conditions that make a planet habitable also make it ideal for scientific discovery. The scientific community largely dismissed this as anthropocentric thinking. Of course we can do science from Earth. We evolved here. Of course the universe is observable from our position. If it weren't, we wouldn't be here asking questions. But then astronomers started actually checking. They started asking, what percentage of potentially habitable locations in the galaxy would provide the same quality of astronomical observations that we have from Earth? The answer was intriguing. Let's start with the basics. To do astronomy, you need transparency. You need to be able to see through the interstellar medium, the gas and dust between stars. Near the galactic center, the stellar density is so high and the dust lanes are so thick that large portions of the sky would be obscured. You could still do astronomy, but you'd have significant blind spots. Whole regions of the galaxy difficult to observe. In the outer reaches of the galaxy, beyond 50,000 light-years, the dust thins out and transparency improves. But there's a different challenge. You're so far from the galactic center and from neighboring galaxies that you have limited perspective on large-scale structures. From Earth's position in the Orion Spur, approximately 26,000 light-years from the galactic center, we have remarkably favorable viewing conditions. We can see the galactic center. Despite the distance, we can observe Sagittarius, a star in infrared and radio wavelengths. We can study the supermassive black hole, the dense star clusters, the complex dynamics of the galactic core. We can see the spiral arm structure. By observing stars and gas clouds at various distances, we've mapped the Milky Way's shape. If we were embedded deep in a major arm, the local dust would significantly obscure our view. If we were in a particularly dusty region, same challenge. We can see the entire sky. Earth's position allows us to look up and down out of the galactic disk with relatively minimal obstruction. This gives us views of the Magellanic Clouds, Andromeda, and billions of galaxies beyond. We can see the cosmic microwave background. The CMB, radiation that formed when the universe was only 380,000 years old, is faint and easily obscured by foreground emission. From Earth, the galactic foreground is manageable. Satellites like WMAP and Planck could filter it out and map the CMB in remarkable detail. In 2014, a team led by Michael Gowanlock at Northern Arizona University ran simulations. They modelled hypothetical planetary systems at various galactic positions and calculated how many would have low enough radiation for complex life, high enough metallicity for rocky planets, clear enough sightlines for optical and radio astronomy, stable enough orbits for long-term evolution. The result? By some estimates, only 0.5% to 1% of the galaxy met all these criteria simultaneously. That's approximately 1 in 100 to 1 in 200. But it gets more specific. Earth isn't just in a position where astronomy is possible. We're in a position where multiple forms of astronomy are possible simultaneously. Optical astronomy, relatively clear sightlines, reasonably dark skies. Radio astronomy, low interference from nearby pulsars and supernova remnants. Infrared astronomy, can peer through remaining dust to see galactic structure. X-ray astronomy, can observe the galactic center and distant active galactic nuclei without overwhelming local sources. Gravitational wave astronomy, stable tectonic environment for building sensitive detectors. Neutrino astronomy, access to deep mines for detectors, moderate cosmic ray background. Each of these requires different optimal conditions. The probability that one location provides favorable conditions for all of them is considerably lower than for any single type. Now, a skeptic would say, this is selection bias. Of course, we're in a location where we can do astronomy. If we weren't, we wouldn't have developed astronomy, and we wouldn't be having this conversation. Fair point. But here's the intriguing part. The ability to do astronomy isn't required for survival. Natural selection doesn't care if you can see distant galaxies. Evolution doesn't favour species that can map the cosmic microwave background. And yet, the same factors that make Earth habitable, low radiation environment, allows complex life and clear observations across multiple wavelengths. Stable climate allows long-term evolution and stable atmospheric conditions for optical astronomy. Chemical richness provides elements for life and for building telescopes and detectors. Also make Earth scientifically well positioned. This correlation is what Gonzalez called the correlation between habitability and measurability, and it's noteworthy. Because in most of physics, different requirements don't necessarily correlate. The conditions for water to remain liquid don't typically correlate with the conditions for, say, clear radio astronomy. They're independent variables, but habitability and measurability, they show significant correlation. It's as if, and I'm treading carefully here because this is where science meets philosophy, it's as if the universe has properties that tend to place observers in contexts where observation is possible. Whether this is pure selection bias, an anthropic effect, or hints at deeper physical principles remains one of the great open questions. There's one more factor at the local scale that's only recently come into focus: dark matter. The invisible substance that makes up approximately 85% of all matter in the universe. We can't see it directly, but we can detect it through its gravitational effects on visible matter. Galaxies are embedded in massive halos of dark matter. These halos provide the gravitational scaffolding that holds galaxies together. Without dark matter, galaxies would likely fly apart. Their rotation speeds appear too high for visible matter alone to hold them together gravitationally. For decades, astronomers assumed dark matter was relatively smoothly distributed within a galaxy's disk, with density increasing toward the galactic center. Smooth distribution, predictable dynamics. Then improved surveys of stellar motions in the Milky Way began revealing more detailed structure, and astronomers noticed something intriguing. Our local region, within approximately 1,500 light-years of the Sun, appears to have a dark matter density somewhat lower than the galactic average at this radius. Some estimates suggest up to 20 to 30% lower, though measurements are still being refined. This is noteworthy for several reasons. Reason 1. Dark matter was expected to be relatively smoothly distributed at this scale. Local density variations of this magnitude were not strongly predicted by standard models. Something about the local environment may have influenced dark matter distribution. Reason 2. Lower dark matter density means somewhat different stellar dynamics. Stars move slightly differently. Gravitational interactions between stars are less influenced by the invisible dark matter component. This could contribute to more predictable and potentially more stable stellar orbits. Reason 3. Lower dark matter density might affect planetary system evolution, though this remains highly speculative. Some theories suggest dark matter particles could occasionally interact with ordinary matter. Lower density would mean less of any such exotic effects. Now, I want to be absolutely clear. The connection between dark matter density and habitability is highly speculative. We don't have confirmed mechanisms. Current evidence is suggestive but not definitive. This is an active area of research, but the observation remains. Our local region appears to have somewhat reduced dark matter density compared to the galactic norm at this radius. This represents another way our local environment differs from the galactic average, though its significance for habitability remains uncertain. So let me ask you a question. When does a pattern of favourable factors stop being pure coincidence? When does "we got lucky" start to feel incomplete as an explanation? We've identified numerous factors: Earth's orbit, Jupiter's configuration, the Moon's presence, our galactic position, our orbital dynamics, the Orion Spur's properties, the local bubble's timing, our observational advantages, even local dark matter density. And in each case, we find ourselves in relatively favourable circumstances. For comparison, your odds of winning the Powerball lottery are about 1 in 292 million. The combined probability we've been calculating, while exact numbers depend on assumptions about independence and estimation methods, we're clearly dealing with an extremely rare configuration. If someone won multiple lotteries in sequence, you wouldn't conclude they were merely lucky. You'd suspect something else was influencing the outcome. So what's influencing Earth's situation? Before we try to answer that, we need to zoom out even further, because the local factors we've discussed, the solar system, the Orion Spur, the local bubble, these are just one level. The real mystery emerges when we look at the Milky Way's history, when we examine where the galaxy came from, how it formed, and when we arrived on the scene. Because it turns out, the Milky Way itself has an unusual history, and the timing of our solar system's formation is, once again, remarkably favourable. Let's go to the galactic scale. Let me tell you a story about our galaxy. It's not the story you learned in school. For most of the 20th century, astronomers thought the Milky Way was ancient and relatively pristine. Sure, it formed billions of years ago from collapsing gas clouds, but once it took its spiral shape, it remained more or less stable. A peaceful island universe, slowly spinning through the cosmos. That story is completely wrong. The Milky Way is a cannibal. In 2018, the European Space Agency's Gaia spacecraft released its second data release, precise positions, velocities, and chemical compositions for over 1.7 billion stars. Astronomers fed this data into supercomputers and asked a simple question: can we trace these stars backward in time? Can we see where they came from? What they found was remarkable. Approximately 10 billion years ago, when the universe was only 3.8 billion years old, a dwarf galaxy roughly 1/4 the mass of the young Milky Way came spiralling inward. Astronomers named this galaxy Gaia-Enceladus, after the giant from Greek mythology. The collision was catastrophic. Gaia-Enceladus ploughed into the Milky Way's disk, shredding itself in the process. Its stars were scattered throughout our galaxy's halo, that diffuse sphere of old stars surrounding the main disk. Today, a significant fraction of stars in the Milky Way's inner halo are remnants of Gaia-Enceladus. But that's not all. The collision triggered something else: massive star formation. When two galaxies collide, Their gas clouds slam together and compress. Compressed gas collapses under its own gravity, forming stars at an accelerated rate. After the Gaia-Enceladus merger, the Milky Way experienced what astronomers call a starburst, a period of enhanced star formation lasting hundreds of millions of years. All those stars, they enrich the galaxy with heavy elements, carbon, oxygen, iron, silicon, all forged in the cores of massive stars and scattered into space when those stars exploded as supernovae. The Gaia-Enceladus collision fundamentally changed the chemical composition of the Milky Way. It contributed significantly to the metallicity, the heavy element content, that would later make rocky planets possible. But Gaia-Enceladus wasn't the only meal. In subsequent years, astronomers using the same Gaia data identified at least 4 other dwarf galaxies that merged with the Milky Way between 12 and 5 billion years ago. The Sagittarius dwarf elliptical galaxy is being consumed right now. It's currently passing through the Milky Way's disk for perhaps the 3rd or 4th time, each passage stripping away more of its stars and gas. Then there's the Helmi stream, the Sequoia galaxy, and evidence of other ancient mergers, all former dwarf galaxies, all now dissolved into the Milky Way's structure. Our galaxy is built from the remnants of numerous smaller galaxies, all accreted over billions of years. Now, here's where this becomes relevant to Earth's story. The Sun is 4.6 billion years old. The Gaia-Enceladus merger happened 10 billion years ago. The major merging period ended approximately 5 billion years ago, shortly before the Sun formed. Timing. Once again, it's about timing. If the Sun had formed 8 billion years ago, during the height of merger activity, our solar system would have faced gravitational chaos. Close passages of stars during mergers can disrupt planetary systems, potentially destabilizing orbits or sending comets into the inner system. Enhanced radiation. Merger-triggered starbursts mean elevated supernova rates. A young Earth would have faced repeated radiation exposure, unstable galactic environment. The Milky Way's overall structure was still settling. The spiral arms were still forming. Orbital dynamics were less predictable. But if the Sun had formed too late, say 1 billion years ago, there could be different challenges related to how metal enrichment from the merger period distributed throughout the galaxy. The Sun formed in a favourable window, after major chaos, during a period of relative stability with good metallicity, and those benefits appear substantial. A 2019 study by Sanjeev Sharma at the University of Sydney analysed the chemical composition of Sun-like stars in the Milky Way. He found that stars with favourable planet-forming chemistry, the right metallicity, the right elemental ratios, show a concentration in the age range of roughly 4 to 6 billion years old. Stars significantly older than 7 billion years, different composition, formed before major enrichment. Stars significantly younger than 3 billion years, different formation context, in regions potentially still affected by recent merger dynamics. The 4 to 6 billion year window represents a relatively favourable period in the Milky Way's history, though not the only possible window. But the merger history may have affected us in another, more subtle way. Remember the Orion Spur, that minor spiral structure we inhabit. Some current models suggest it may have formed or been significantly shaped as a result of the Gaia-Enceladus merger and its aftermath. When Gaia-Enceladus ploughed through the Milky Way's disk, it didn't just trigger star formation, it also potentially disrupted the existing spiral structure. The collision may have redistributed mass, changed orbital dynamics, and influenced density wave patterns. The Orion Spur, the stable intermediate structure that provides us with reduced supernova exposure, might be partially a consequence of that ancient collision. The galaxy's violent past may have helped create the favourable present we inhabit. Now we need to talk about the elephant in the room. The question that's been hovering over this entire discussion. If Earth's location represents such a favourable configuration, where is everybody else? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" If the universe is so vast, so old, with billions of potentially habitable planets, why haven't we detected any signs of alien civilizations? For decades, scientists proposed various solutions. Maybe intelligent life is rare. Maybe civilizations destroy themselves quickly. Maybe they're deliberately hiding. Maybe interstellar communication is harder than we think, but there's another possibility, one that our journey through the Milky Way makes increasingly plausible. Maybe the zone truly favourable for complex technological life is much smaller than optimistic estimates suggest. Let's consider the cumulative effect of the factors we've discussed. Galactic habitable zone, approximately 20% of stars, proper distance from centre. Circular galactic orbit, approximately 5 to 10% of stars, avoiding major spiral arms. Post-merger stability, favourable timing in galactic history. Minor spiral structure, being in calmer interarm or spur region. Local environmental factors, favourable supernova timing, radiation environment. Stellar type, Sun-like G or K-type stars, planetary system. Configuration, rocky planet with favourable orbit, outer gas giant, large moon. When you combine these factors, even with generous estimates, the fraction of locations truly optimal for complex life becomes quite small. If we conservatively estimate that only a small percentage of stars meet all these combined criteria, we might be looking at thousands to tens of thousands of potentially favourable stellar systems in the Milky Way. But add stellar type filters and planetary system requirements, and the number drops significantly. This is called the rare Earth hypothesis, formalised by Peter Ward and Donald Brownlee in 2000. The idea that while microbial life might be relatively common, complex multicellular life, and especially intelligent technological life, may be extraordinarily rare due to the cumulative requirements. Here's where it gets philosophically interesting. If technological civilizations are extremely rare, perhaps only a handful per galaxy, then the Fermi Paradox largely dissolves. We haven't heard from aliens because there may not be many nearby. The nearest technological civilization might be tens of thousands of light years away, or even in another galaxy entirely. Radio signals would take tens of thousands of years to reach us. If they're sending signals now, we won't receive them for tens of thousands of years. We might not be in a crowded cosmic neighbourhood. We might be in a cosmic frontier, an isolated oasis with vast distances to the next one. But this creates an interesting question that philosopher Nick Bostrom has explored: the observation selection effect. If intelligent observers are extremely rare, then observers will necessarily find themselves in the rare circumstances that permit observation. You can't observe the universe from a location that doesn't support observers. This seems to resolve part of the mystery. Of course we're in a favourable location, we couldn't be anywhere else. But there's a nuance here that deserves attention. The anthropic principle explains why we observe conditions compatible with our existence. But it doesn't necessarily explain why habitable conditions would correlate with observational advantages. Our location isn't just habitable, it's also well positioned for comprehensive astronomy. We can observe multiple wavelengths, see deep into space, map cosmic structure. Why should those factors correlate? Natural selection rewards survival and reproduction. It doesn't reward the ability to measure the cosmic microwave background or map distant galaxy clusters. The capacity for advanced science isn't obviously necessary for survival, and yet, the factors that make Earth habitable, stable radiation environment, clear sightlines, chemical richness, also make Earth scientifically well positioned. This correlation is what keeps some cosmologists pondering. This is where pure materialism feels incomplete to some thinkers, because it hints, and I'm choosing words carefully here, it hints that the universe may have properties that tend to produce observers in contexts where observation and comprehension are possible. Whether this is pure selection effect, hints at deeper physical principles, or something else entirely, remains one of the great open questions. But we're not done with the galactic scale yet, because there's one more factor we need to discuss, one that operates on an even larger scale than the Milky Way itself. Our galaxy isn't static, it's moving, and where it's moving reveals another layer of cosmic context. In the 1970s, astronomers noticed something intriguing. The Milky Way is moving through space at approximately 600 kilometers per second relative to the cosmic microwave background, essentially the rest frame of the universe. That's over 2 million kilometers per hour. We're racing through space. But where are we going? By mapping the velocities of thousands of nearby galaxies, astronomers triangulated the answer. We're being gravitationally drawn toward a massive concentration of matter approximately 150 million light-years away, in the direction of the Hydra-Centaurus supercluster. They called it the Great Attractor. As mapping improved, astronomers realized the Great Attractor is actually part of something even larger, the Laniakea supercluster, a structure containing 100,000 galaxies spanning 520 million light-years. Our local group, the cluster containing the Milky Way, Andromeda, and about 50 dwarf galaxies, sits on the edge of Laniakea, being drawn slowly toward the center. But here's what's relevant to our story. This motion is relatively stable and gradual. We're not being pulled into an imminent catastrophic collision. We're not plunging into a dense galaxy cluster where tidal forces would rip the Milky Way apart. We're in a long, slow gravitational flow that will take hundreds of billions of years to play out significantly. Compare this to galaxies in the core of massive clusters like Coma or Virgo. In those environments, galaxies collide more frequently. Stars can be stripped away by tidal forces. Gas is heated by cluster dynamics, sometimes preventing new star formation. Those are not ideal environments for long-term biological evolution. But the Milky Way, we're in a relatively quiet part of the cosmic web, on the edge of a supercluster, not in its chaotic core. This provides stability. And there's one more timing factor worth noting. In approximately 4 billion years, the Milky Way will collide with the Andromeda galaxy. This has been confirmed through Hubble Space Telescope observations showing Andromeda approaching us at about 110 kilometers per second. The collision will be dramatic. Both galaxies will eventually merge into a single, larger elliptical galaxy. But here's the timing consideration. This collision will happen roughly 4 billion years from now. The Sun will become a red giant in approximately 5 billion years, expanding to potentially engulf Earth's orbit. The galactic collision happens before the Sun's demise, but not so soon that the initial gravitational perturbations significantly disrupt Earth now. If the Andromeda collision were happening now, the gravitational perturbations could potentially destabilize the Oort cloud, the sphere of icy bodies surrounding our solar system. This could increase comet influx and impact rates. If the collision had happened 2 billion years ago, it might have influenced the environment during critical periods of complex life's evolution on Earth. But the collision timing is such that Earth's biosphere has had billions of years of relative galactic stability to develop complex life. And the major disruptions occur around the time our star becomes inhospitable anyway. From a biological evolution perspective, the timing is favourable. Take a breath. I know this is a lot. We've examined layers from Earth's orbit to the structure of the cosmic web, and at each level, we found favourable configurations. You might be feeling uncertain. You might be thinking, what does this all mean? Is this just selection bias? Or is there something deeper? These are exactly the right questions, and we're going to confront them directly. We still have more to explore. We're going to examine competing explanations for these patterns, pure chance and selection bias, anthropic reasoning, or hints of deeper physical principles we don't yet understand. And we're going to explore what happens when science reaches the boundary between data and interpretation, where physics meets philosophy. But before we get there, there's one more dimension we need to consider, the temporal aspect. Not just when our solar system formed, but when in cosmic history we find ourselves. Because it turns out, the universe itself may have a favourable zone, not just in space, but in time. Let's continue this journey. All right, we need to address the elephant in the room. Isn't this just the anthropic principle? Of course we're in a habitable location. If we weren't, we wouldn't be here to observe it. This whole argument is circular reasoning. This is the standard objection, and it's a good one. So let's examine it carefully, because this is where science bumps up against philosophy, and where a lot of scientists get uncomfortable. The anthropic principle comes in two flavours, the weak. Anthropic principle says the observed values of physical and cosmological quantities are not equally probable, but take on values restricted by the requirement that there exist sites where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. In plain English, we observe what we observe because we exist. Selection bias explains everything. If conditions weren't right for observers, there'd be no observers to notice. The strong anthropic principle says, the universe must have properties that allow life to develop within it at some stage in its history. This version implies, depending on interpretation, that the universe is somehow required to produce observers. It edges uncomfortably close to purpose or design, which is why most physicists reject it. Most scientists embrace the weak anthropic principle. It's philosophically safer. It doesn't imply anything supernatural or teleological. It's just selection bias, statistics, and logic. But here's the interesting tension with applying the weak anthropic principle to Earth's location. The anthropic principle explains why we observe habitable conditions, but it doesn't necessarily explain why habitable conditions would correlate with other, seemingly unrelated properties. Let me break this down with an analogy. Imagine you wake up in a hospital. You're alive, conscious, and able to think. The anthropic principle explains why you observe yourself in a hospital. If you died, you wouldn't be observing anything. Being alive is a prerequisite for observation. But now imagine you notice something else. The hospital you're in happens to have an exceptionally comprehensive medical library, an unusually complete collection of medical knowledge, far more than would be typical. The anthropic principle explains why you're in a hospital. You needed medical care to survive. But it doesn't explain why that same hospital would also have exceptional educational resources. Being alive requires medical care. It doesn't require access to extensive medical knowledge. Those are somewhat independent things, and yet you find yourself in a place with both. That's analogous to the situation with Earth. Habitability requires stable orbit, appropriate distance from star, radiation shielding, chemical richness, stable climate. Scientific measurability requires low dust obscuration, clear sightlines, multiple wavelength accessibility, stable observing platform, diverse astronomical phenomena, visible. These are different requirements, and yet they show significant correlation in Earth's location. Guillermo Gonzalez analysed this correlation. His work suggested that galactic positions favourable for habitability tend to also be favourable for observing galactic structure. Stellar system configurations favourable for stable planets tend to also be favourable for certain types of astronomical observation. Temporal epochs, favourable for complex chemistry, tend to also be favourable for observing cosmic history. The strength of this correlation is noteworthy, though the exact coefficients and mechanisms remain subjects of ongoing debate. But what could cause habitability and measurability to correlate? The anthropic principle explains why we observe habitable conditions, but it doesn't immediately explain why we'd also observe scientifically privileged conditions, unless comprehension itself somehow aids survival, which is an interesting question for evolutionary biology. And there's another consideration. Remember the local bubble, the cavity carved by supernovae that we happen to be positioned near. That bubble may be providing some cosmic ray shielding, but it's also giving us something else, a relatively clear view of nearby star-forming regions. The young stars within several hundred light years, the ones we study to understand planet formation, are largely located on the bubble's surface. They're arranged at roughly similar distances in a shell-like distribution. This makes comparative stellar studies somewhat easier than if young stars were randomly scattered at varied distances throughout a dusty medium. Is this required for life? No. Does it aid our ability to understand stellar and planetary formation? Yes. The correlation between habitability and scientific observability is what Gonzalez found noteworthy, and it raises interesting questions. So we're left with several possible frameworks. Framework 1, pure selection effect. We're in a favourable location simply because observers can only exist in favourable locations. The correlation between habitability and measurability is either coincidental or there's a subtle evolutionary advantage to comprehension we haven't identified. This is the most conservative interpretation. Framework 2, anthropic selection plus multiverse. There are many or infinite regions with randomly distributed conditions. Most observers are in less than optimal positions. We happen to be in a particularly favourable one. Selection bias explains everything, though we can't directly test this hypothesis since we can't observe other regions or universes. Framework 3. Physical principles we don't yet understand. The universe has physical laws or structural properties that naturally tend to produce observers in comprehension-friendly contexts. This isn't design in a theological sense, but rather a deep property of physics, perhaps related to how complexity emerges, how information is structured, or principles we haven't yet discovered. This is the most speculative but potentially most scientifically interesting framework. We're not just alive. We're alive in a position that enables understanding of our cosmic context. The universe isn't just producing consciousness, it's producing consciousness in contexts where consciousness can comprehend the system that produced it. Whether this is pure selection bias, hints at deeper physical principles, or something else entirely, that's the open question. But one thing is clear: science is about examining patterns, and this is a pattern worth taking seriously. There's one more framework we should consider, even though it might sound like science fiction. What if we're in a simulation? The simulation hypothesis, formalized by philosopher Nick Bostrom in 2003, proposes that we might be living in a computational simulation created by an advanced civilization. Bostrom's argument has an interesting logical structure. Premise 1. If civilizations can reach a technological level where they can simulate conscious beings, some probably will. Premise 2. A sufficiently advanced civilization could potentially run many simulations, perhaps simulated histories of their own evolution. Premise 3. If many simulated realities could exist for every one base reality, then statistically, most conscious observers would be in simulations rather than base reality. Most scientists regard this as interesting philosophy, but note it's unfalsifiable, which makes it scientifically problematic. But here's why it's relevant to our discussion. If you were designing a simulation to study the emergence of intelligence and scientific understanding, where would you place your simulated observers? You'd likely place them in a location that's habitable, so they survive long enough to develop complexity, observable, so they can develop science and technology, comprehensible, so they can understand their cosmic context. You'd want your simulated civilization to discover physical laws, to map their galaxy, to develop cosmology, because that might be part of the simulation's purpose, to study how intelligence emerges and how it comes to understand reality. A simulation designer probably wouldn't place observers in a galaxy's chaotic core where they're constantly disrupted. That simulation would be less interesting. Life keeps getting reset before achieving complexity. A simulation designer probably wouldn't place observers in a heavily dust-obscured region where they can't observe much beyond their local environment. That would limit what the simulated intelligence could discover. From a simulation design perspective, Earth's location, safe enough to evolve, positioned to observe in an era where the universe is comprehensible, would make sense. Now, to be absolutely clear, this doesn't mean we are in a simulation. The simulation hypothesis remains unfalsifiable and highly speculative. But it does make an interesting point. If we're in a simulation, we'd expect to find ourselves in a statistically unusual but scientifically optimal location. And that does describe our situation. Does this prove simulation? Of course not. Correlation isn't proof of anything, but it's another framework for thinking about the pattern we've observed. The philosopher David Chalmers has argued that even if we're in a simulation, the physics would still be real to us. The observations would still be valid. Science would still work. The simulation hypothesis doesn't undermine science, it just reframes what reality means. But it would suggest something profound. Our existence might not be accidental. It could be, in some sense, intentional, not necessarily in a religious sense, but in the sense that there might be reasons, computational, scientific, or otherwise, why observers exist in observer-friendly contexts. This brings us to perhaps the most widely discussed framework in physics, the multiverse, multiple universes with varying properties. It's become a common explanation for cosmic fine-tuning in physics, a way to explain why our universe has properties compatible with life. Here's the basic argument. If there are many universes with different physical constants, initial conditions and structures, then some universes will randomly have properties that allow observers. We find ourselves in one of those universes because we couldn't exist in any other kind. The fine-tuning we observe, the cosmological constant, the strength of fundamental forces, the properties of particles, might just be random variation across the multiverse. We observe a winning ticket because only winning tickets produce observers. This is sometimes called the anthropic landscape in string theory. It's popular among theoretical physicists because it addresses multiple fine-tuning problems simultaneously. But the multiverse hypothesis has limitations. Testability challenge. By definition, other universes, if they exist, are causally disconnected from ours. We can't observe them, can't test their properties, can't verify they exist. This makes the hypothesis scientifically problematic. It's not falsifiable in the traditional sense. Some physicists argue that the multiverse emerges naturally from inflation theory or certain interpretations of quantum mechanics. These connections give it more scientific standing than pure speculation, but the observational challenges remain. The scope problem. Even if the multiverse explains why our universe has the right physical constants, it doesn't directly explain why we, observers within this universe, are in such a favorable location within it. Multiverse theory explains cosmic scale fine-tuning, why the universe permits life at all. But it doesn't necessarily explain galactic scale, stellar system scale, or planetary scale favorable factors, why we're in this specific, unusually favorable location. You'd need something like a nested explanation, many universes, each with many possible observer locations, and we happen to be in both a life-permitting universe and an unusually favorable location within it. The pattern question. If observers consistently end up in comprehension-friendly locations, that itself might hint at a deeper pattern, perhaps a meta-principle about how complexity or observers emerge in physical systems. The challenge is, how do we think scientifically about these questions? Here's what we know. We've examined numerous factors: Earth's orbit, Jupiter's configuration, the Moon's presence, our galactic position, our orbital dynamics, the Orion Spur's properties, the local bubble's timing, our observational advantages, and in each case we find ourselves in relatively favorable circumstances. Each individual factor might be explained by selection bias, but the correlation of multiple independent factors, especially the correlation between habitability and measurability, is more puzzling. Three general approaches emerge. 1. Conservative interpretation. Pure selection bias explains everything. The correlations are either coincidental or we're missing evolutionary reasons why comprehension aids survival. 2. Multiverse interpretation. Many possible observer locations exist, across universes or within ours. We're in a favorable one. Selection bias explains the rest. 3. New physics interpretation. There might be physical principles we don't yet understand that naturally tend to produce observers in comprehension-friendly contexts. This would be testable if we find other examples of life. None of these interpretations is definitively proven. Each has strengths and limitations. What's clear is this: science is about taking patterns seriously, about following evidence where it leads, about asking hard questions even when they lead to philosophical territory. And the evidence points to something genuinely intriguing. We exist in a location that is both favourable for life and favourable for understanding. Whether that's pure chance, selection bias, hints of deeper physics, or something else entirely, that's the open frontier. We're at the boundary between what we can observe and what we can only theorise about. It means we should be curious. These patterns are fascinating regardless of their ultimate explanation. They tell us something about our cosmic context worth understanding. It means we should be careful. If Earth represents a genuinely rare configuration, whether through pure chance or deeper reasons, then we have a responsibility to preserve it. This isn't about religion or philosophy, it's about recognizing something potentially precious when we encounter it, for better understanding of our own circumstances, for answers to these deep questions about observers and observability. And it means we should remain scientifically honest, not claiming certainty where we have only hypotheses, not dismissing patterns just because they're philosophically uncomfortable, but following the evidence where it leads. Because whatever the ultimate explanation, pure chance, Anthropic selection, simulation, new physics, or something we haven't imagined, the pattern itself is real, and it's worth taking seriously. Now let me show you something that adds another dimension to our understanding: time. The galactic habitable zone, that favourable region between roughly 20,000 and 30,000 light-years from the galactic centre, isn't static, it moves. And understanding this temporal dimension reveals why when matters as much as where. Here's how it works. In the early universe, the first few billion years after the Big Bang, there were almost no heavy elements. The first stars formed from nearly pure hydrogen and helium. When they died, they scattered the first carbon, oxygen, and iron into space. But it took time for these elements to accumulate. For the first several billion years of the universe's existence, forming rocky planets anywhere would have been extremely difficult. There simply wasn't enough silicon, iron, and nickel. Most planets would be gas giants or ice worlds. No solid surfaces, no geology, no plate tectonics, no life as we know it. This is called the metallicity constraint, and it applies to every galaxy, including the Milky Way. But as the galaxy aged, as more stars lived and died, heavy elements accumulated. The metallicity increased over time, and the galactic habitable zone gradually expanded outward from the galactic centre like a ripple spreading across a pond. Australian astrophysicist Charles Lineweaver mapped this expansion in an influential 2004 paper. His analysis suggested that 8 to 10 billion years ago, the favourable zone was concentrated closer to the galactic centre, roughly 15,000 to 20,000 light-years from Sagittarius, a star. But this zone faced challenges: elevated radiation, more frequent stellar encounters. Life might form, but conditions were more challenging. 6 to 8 billion years ago, the zone expanded outward to approximately 18,000 to 25,000 light-years. Conditions were improving as the galaxy settled from major merger activity. 4 to 6 billion years ago, the zone reached approximately 20,000 to 30,000 light-years, where we are. This represents a particularly favourable era. Far enough from the centre for safety, sufficient metallicity for rocky planets, merger activity largely settled, spiral arms well defined. Future, 2 to 4 billion years from now, the zone will continue expanding outward to approximately 25,000 to 35,000 light-years. Our current location may become less favourable as the galactic environment slowly evolves. We're not just in a favourable place, we're in a favourable place at a favourable time. The habitable zone appears to have swept through our location around the time our solar system was forming 4.6 billion years ago. Think about the implications. If the Sun had formed significantly earlier, say 3 billion years earlier, it would have formed before optimal metallicity reached our galactic radius. Earth-like planets would be less likely. If the Sun formed significantly later, say 2 to 3 billion years from now, our location may be entering a less favourable phase as the galaxy continues to age and evolve. The temporal window of maximum favourability spans several billion years of the Milky Way's 13 billion year history. We formed during this window. Lineweaver's work went further. He didn't just calculate when and where the habitable zone exists. He modelled when and where Earth-like planets are most likely to form. His analysis suggested that peak probability for Earth-like planet formation occurred approximately 4 to 6 billion years ago at galactic radii between roughly 24,000 and 28,000 light-years. Our Sun, at approximately 26,000 light-years, formed 4.6 billion years ago. We're within the peak window both spatially and temporally for favourable planet formation conditions in the Milky Way's history. This temporal dimension adds another layer to the pattern we've been exploring. Not just where we are, but when we arrived on the scene. Now I want to address something fundamental that goes deeper than physics or astronomy, into the realm of philosophy and consciousness. Why can we understand any of this? Think about what we've done in this exploration. We've calculated orbital mechanics across billions of years, mapped galactic structure from inside the galaxy, traced the history of mergers that happened billions of years before we existed, predicted the future evolution of the galactic habitable zone, developed quantum mechanics, relativity, cosmology. But here's the thing. We're primates. We're apes who evolved on the African savanna to avoid predators, find food, and reproduce. Natural selection shaped our brains for survival, for tracking animals, forming social bonds, making tools, planning hunts. And yet, we can comprehend quantum field theory, we can map the cosmic web, we can understand space-time curvature, the mathematics we developed for practical purposes, counting, measuring, calculating, turns out to describe the fundamental structure of reality. The logic we evolved for survival turns out to unlock the deepest secrets of the universe. The pattern recognition that helped us survive turns out to reveal cosmic patterns spanning billions of light years. This is what physicist Eugene Wigner called the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical concepts describe the fundamental workings of reality so precisely? Einstein captured the mystery. The most incomprehensible thing about the universe is that it is comprehensible. But it's not just that the universe is comprehensible. It's that we exist in a location and era where comprehension is particularly enabled. Consider the correlations. Optical observation. Our location has relatively low dust obscuration. Our atmosphere is transparent at optical wavelengths. Our star emits primarily in the optical range, which is why our eyes evolved optical sensitivity. Radio astronomy. Earth's ionosphere allows certain radio frequencies through, frequencies where hydrogen, the universe's most common element, emits. Our location has relatively low interference from nearby pulsars. Radio astronomy becomes possible. Stable platform. Earth's rotation rate allows long exposure observations. Our atmosphere provides protection while remaining mostly transparent. Our magnetic field shields us from solar wind without interfering with sensitive instruments. Our geology is stable enough for precision instruments. Cognitive capacity. Human brains appear overbuilt for pure survival. We have abstract reasoning, mathematical thinking, long-term planning far beyond what basic survival seems to require. Why did evolution give us brains capable of understanding quantum mechanics when that provides no survival advantage? Temporal window. We exist during an epoch when the cosmic microwave background is detectable but not overwhelming. Too early in cosmic history, the CMB would be too bright. Too late, it would be redshifted beyond easy detection. We're in the window where observational cosmology is possible. Each of these factors involves different physical systems: galactic structure, planetary atmosphere, stellar physics, evolutionary biology, cosmic history. They're largely independent, and yet they align to enable comprehensive understanding of our cosmic context. Physicist Paul Davies has explored this correlation extensively. In his work, he suggested that this pattern hints at something deeper about the nature of physical law, not supernatural design, but perhaps fundamental properties of how complexity and information emerge in physical systems. Some proposals suggest that the laws of physics might naturally favor configurations where complex information processing systems like brains can emerge, and that such systems would tend to arise in contexts where they can gather information about their environment effectively. This is highly speculative. Most physicists regard it as interesting philosophy rather than testable physics. We don't know how to test these ideas. We don't have equations that predict this pattern. But the correlation remains noteworthy. Habitability correlates with measurability. The conditions that allow life correlate with conditions that allow scientific understanding. Is this pure coincidence? Inevitable selection bias. We can only observe what we can observe. Subtle evolutionary advantage. Comprehension aids survival in ways we underestimate. Hint of deeper physical principles we don't yet understand. That's the open question at the frontier of science and philosophy. What's clear is this: we exist, we can observe, we can comprehend, and our location enables all three in remarkable ways. Journeying through space and time, from Earth's orbit to the structure of the universe. We've explored pattern after pattern, correlation after correlation. Now it's time to come home, to ask the most personal question: so what? What does this mean for you? For your life? For humanity's choices in the coming decades and centuries? Let's bring this cosmic journey back to Earth. Remember where we started? With Carl Sagan's pale blue dot photograph, with his words about Earth being a mote of dust suspended in a sunbeam. Sagan used that image to argue for humility, to show us our cosmic smallness, to demonstrate that we're not the center, not special, not cosmically central. And he was right about the humility part. We should be humble. The universe is vast beyond comprehension. Our planet is tiny. Our lives are brief. Our species is young. But there's another way to look at that same photograph, one informed by everything we've explored together, because smallness and rarity are not the same thing. Yes, Earth is physically tiny, 12,742 kilometers in diameter, compared to the universe's 93 billion light-year observable expanse. We are infinitesimally small, but we may also be extraordinarily rare. Based on the factors we've examined, planetary configuration, galactic position, temporal window, local environment, locations truly favourable for complex technological life appear to be uncommon in our galaxy. Imagine holding a single grain of sand, one grain among all the beaches on Earth. That grain is tiny, yes, but if it were one of very few grains with a particular rare crystalline structure found almost nowhere else, would you call it insignificant, or would you call it precious? Earth may be precious, not because we're at the centre, not because the universe revolves around us, but because we may be part of a genuinely rare phenomenon. And rarity suggests responsibility. When Sagan looked at the pale blue dot, he saw the smallness of human concerns against the vastness of space. He wanted us to realise that our conflicts, our divisions, our territorial disputes are cosmically meaningless. But I look at that same photograph with everything we've learned, and I see something complementary. I see the only known location in the universe where matter has organised itself to understand matter, where atoms have arranged themselves to contemplate atoms, where the universe has become conscious of itself. I see 4.6 billion years of cosmic history, stars forming and dying, galaxies evolving, heavy elements accumulating, a solar system coalescing in a favourable location, all leading to this moment. To you, watching this, comprehending the journey that led to your existence. Every atom in your body is a relic of cosmic history. The calcium in your bones was forged in dying stars. The iron in your blood was scattered by supernova explosions. The oxygen you breathe was produced by stellar fusion in stars that lived and died before our sun was born. You are not outside the universe looking in. You are the universe experiencing itself from within. You are 13.8 billion years of cosmic evolution achieving self-awareness. That's not insignificant. That's remarkable. Not miraculous in a supernatural sense, but remarkable in being statistically rare and profoundly meaningful. Sagan wanted us to realise we're not cosmically central, so we treat each other better, so we transcend our tribal conflicts. But perhaps we can integrate both perspectives. We should treat each other better and preserve our rare circumstances. Because we're carrying something potentially precious, consciousness, comprehension, the universe's capacity to know itself, and we shouldn't squander it on division and destruction. Perhaps the lesson of the pale blue dot isn't just we're cosmically small, perhaps it's also we're potentially cosmically rare, and that matters. So here we are, near the end of our journey. We've examined evidence, we've explored patterns, we've confronted puzzling correlations. Now comes the interpretive question. What does it mean? Let me present 3 frameworks for thinking about what we've discovered. Framework 1. Statistical inevitability. This is the conservative scientific position. We're in a favourable location because given enough possibilities, even rare configurations must occur somewhere. The logic. Even if favourable configurations are extremely rare, with enough planets in enough galaxies, some will exist. The observable universe contains trillions of galaxies, each with billions of stars. Even very low probabilities become certainties at cosmic scales. We exist in one of those rare locations. Selection bias ensures observers only exist in observer-permitting conditions. Strengths. Requires no new physics, aligns with principle of mediocrity, we're not fundamentally special, philosophically straightforward limitations, doesn't fully explain habitability, measurability, correlation, doesn't address why observers emerged when where they did in cosmic history, feels incomplete as explanation for multiple correlated factors. Framework 2. Anthropic reasoning plus multiverse. This is common among theoretical physicists. Many or infinite universes exist with varying properties. Only universes with suitable physics permit observers. We necessarily find ourselves in such a universe. Extended to local scale, within any life-permitting universe, observers will necessarily find themselves in rare locations suitable for observation. Selection effects explain everything. Strengths addresses cosmic fine-tuning elegantly, emerges from certain interpretations of quantum mechanics and inflation theory, resolves apparent specialness limitations, unfalsifiable, cannot observe other universes, requires accepting unobservable realities, still doesn't fully explain within universe correlations. Some view it as explanation avoidance. Framework 3. Emergent physical principles. This is the most speculative framework. Perhaps physical laws have properties that naturally favour observer emergence in observation-friendly contexts, not through conscious design, but through deep mathematical structure of physical law, similar to how water molecules naturally form hexagonal ice crystals without intending to. Emergent order from underlying principles. This would suggest, when matter achieves complexity sufficient for consciousness, it tends to emerge in contexts where environmental observation and comprehension are possible, not by design, but by physical principle. Strengths. Testable in principle, predicts patterns should repeat if we find other life, explains habitability, measurability correlation, points toward potentially discoverable new physics, avoids multiverse's unfalsifiability. Limitations. No current theoretical framework supports it, requires accepting we don't understand fundamental principles, sounds superficially similar to teleological arguments, though distinct. So which framework is correct? We don't know. This is the frontier where data meets interpretation, where physics meets philosophy. But the question matters. It shapes how we understand ourselves, how we value our circumstances, how we think about cosmic purpose, if any exists. If Framework 1 is correct, we're products of statistical inevitability. Life has whatever meaning we create. We're free to define purpose in an indifferent universe. If Framework 2 is correct, we're one of many observers across the multiverse. Special to ourselves, perhaps typical in the broader landscape. If Framework 3 is correct, we're part of a physical process by which the universe develops comprehension of itself. Meaning would be something we discover, not create. Each framework suggests different ethics, priorities, and visions of humanity's future, and we don't yet know which, if any, is correct. But there's one area where this research has immediate practical implications: the search for extraterrestrial life. For decades, SETI, the search for extraterrestrial intelligence, has been listening for signals from nearby stars. The assumption has been, if technological civilizations are common, we should detect something. We haven't. The silence continues. This has led to increasingly conservative estimates about the prevalence of intelligent life. But perhaps we should reconsider where we're searching. Everything we've explored suggests complex technological life requires specific conditions: favorable planetary system configuration, favorable galactic location and orbital dynamics, favorable cosmic timing and local environment. If these factors genuinely matter, we should focus our search accordingly. Starting in the 2030s, next-generation telescopes will revolutionize our capabilities. The extremely large telescope in Chile, the 30-meter telescope, pending resolution of construction issues, the Nancy Grace Roman Space Telescope, the Habitable Worlds Observatory. These instruments will be capable of directly imaging exoplanets and analyzing their atmospheres for biosignatures: oxygen, methane, water vapor, potentially even industrial signatures. But which exoplanets should we prioritize among the thousands we've discovered? Based on our exploration, a refined target list might include only planets where 1. The host star is Sun-like, G or K-type. 2. The star is in its galaxy's habitable zone, appropriate distance from galactic center. 3. The star has relatively circular galactic orbit, avoiding regular spiral arm crossings. 4. The star is in a calmer region, not a major spiral arm. 5. The planet has nearly circular orbit in the habitable zone 6. Evidence suggests a gas giant exists in the outer system. Applying these filters dramatically narrows the target list, from thousands to perhaps dozens or hundreds of highest priority candidates. That's actually advantageous. It makes the search focused and achievable within decades rather than centuries. And here's why this matters profoundly. If we find life elsewhere, and it's also in a location that's both habitable and scientifically favourable for observation, that would be extraordinary evidence. It would suggest the pattern we've observed isn't unique to Earth. If that pattern repeats, it points toward Framework 3. That physical law might naturally favour observer emergence in comprehension-friendly contexts. That would be among the most profound scientific discoveries possible. It would transform our understanding of what the universe is and whether it has directionality or purpose in any meaningful sense. And we might have preliminary answers within our lifetimes. The search for life isn't just about finding aliens, it's about understanding whether Earth represents a cosmic accident or a cosmic pattern, whether we're alone in our circumstances, or whether the universe naturally produces observers who can comprehend their cosmic context. That's a question worth pursuing. We've journeyed from Earth's orbit to the edge of the observable universe. We've explored patterns that are fascinating regardless of their ultimate explanation. Now, in our final moments together, let's bring this cosmic journey back to the most personal level. What does it mean for you? All right, let's bring this home. Let's talk about you. Not humanity in the abstract, not civilization as a concept. You, the person watching this right now. You are made of atoms that were forged in the cores of dying stars billions of years ago. Every element heavier than helium in your body, carbon, nitrogen, oxygen, calcium, iron, came from supernova explosions. But it's not just that you're made of stardust. That's the poetic version, the bumper sticker version. The full version is this. Your atoms were forged in stars that lived and died during specific eras of galactic history. They were scattered into space and eventually concentrated in a region of the galaxy, the Orion Spur, that represents a relatively stable, favourable environment. They were incorporated into a molecular cloud that collapsed approximately 4.6 billion years ago, forming the Sun and planets. One of those planets, Earth, formed at a favourable distance from the Sun, in a nearly circular orbit that provided climate stability. The solar system formed in a galactic location with favourable environmental characteristics, moderate radiation, clear observational access, relative safety from major disruptions. And after 4 billion years of evolution, mass extinction survived, evolutionary branches explored, climate changes weathered, your direct ancestors emerged. Every single one of your ancestors, stretching back through billions of years, survived long enough to reproduce. An unbroken chain of survival stretching back through time. Single-celled organisms, multicellular life, fish, amphibians, reptiles, mammals, primates, hominids, Homo sapiens, through recorded history, through your parents, to you. You are the product of an extraordinarily long contingent journey, and now, equipped with a brain that evolved for survival but gained the capacity for abstract thought, you can comprehend this journey. You can understand stellar nucleosynthesis. You can calculate orbital mechanics. You can map galactic structure. You can look back 13.8 billion years to the cosmic microwave background. You contain approximately 7 octillion atoms, each with its own quantum properties, all coordinating to produce consciousness. Your brain contains 86 billion neurons, each connected to thousands of others, forming roughly 100 trillion synapses. The number of possible neural states is astronomical. You are among the most complex structures we know of in the cosmos, and you exist in a location where that complexity can comprehend its own cosmic context. Should you feel insignificant? I'd argue you shouldn't. You might feel awed by the cosmic journey that led to this moment. You might feel grateful to experience consciousness at all, let alone consciousness in an era and location where the universe is comprehensible, and perhaps you should feel thoughtful about responsibility. Because if Earth genuinely represents a rare configuration, whether through chance, selection, or deeper principles, then we have something potentially precious. We face real challenges: climate change threatening our biosphere, nuclear weapons threatening sudden catastrophe, resource conflicts threatening stability. The universe, through billions of years of cosmic evolution, has produced in you the capacity for awe, for wonder, for comprehension. How we use those capacities matters. So here's my question to you. What will you do with this perspective? You might regard it skeptically, view the patterns as selection bias and coincidence, return to your daily life largely unchanged, maintaining that Earth is cosmically typical. That's a valid response. Take it seriously. Consider that you're part of something genuinely rare and worth preserving. Let it inform how you see yourself, your species, and your choices. That's also valid. Investigate further. Pursue science, astronomy, astrobiology. Become part of the generation that helps answer, are we alone? How common are favourable configurations? What do the patterns mean? This too is valid. There's no single correct response. But there is your honest response, based on what resonates with you. What does it make you want to do? I'm genuinely curious how this journey affects different people. Does it make you feel small or significant, anxious or inspired, skeptical or convinced? The conversation itself, this collective human attempt to understand our place in the cosmos, is part of how consciousness explores its own nature. Every discussion, every question raised, every perspective shared, contributes to our species' attempt to comprehend its context. You're participating in that exploration right now, and that's valuable. One final thought. This journey, Earth's journey through the Milky Way, isn't over. It's ongoing. You're on the journey right now. Right at this moment, Earth is moving through space at 30 kilometers per second relative to the Sun. The Sun is moving through the galaxy at approximately 220 kilometers per second. The galaxy is moving through the universe at roughly 600 kilometers per second. You're on a cosmic vessel, following an orbit that takes 225 to 250 million years to complete around the galactic center. 1 galactic year ago, the last time our solar system was at roughly this position in the Milky Way, dinosaurs had not yet evolved. The most complex life on Earth was early reptiles. 1 galactic year from now, 225 million years in the future, what will Earth be? Will humans still exist? Will we have spread to other worlds? Will we have answered the questions we've explored today? Or will we be gone, a brief flash of consciousness in the galaxy's long history? The answer depends partly on choices made in the coming centuries. In your lifetime, the telescopes we're building now, the James Webb, the Extremely Large Telescope, upcoming missions, will determine whether we find biosignatures elsewhere, whether we confirm or challenge the patterns we've discussed. The actions we take regarding climate, resources, and cooperation will determine whether Earth remains favourable for technological civilization in the coming centuries. The scientific investments we make will determine what we learn about our cosmic context. You are living during a significant moment. When one species achieves sufficient technology to ask these questions and enough knowledge to begin answering them, the universe took 13.8 billion years to produce conscious matter capable of comprehending the universe that produced it. What we do with that capacity matters. So here's my final message. You are part of something potentially rare. You are part of a journey that began with the Big Bang. The journey through the Milky Way that reveals our place among the stars isn't just Earth's journey, it's your journey. Make it meaningful. If you made it this far, thank you. Your remarkable home in a vast universe. Subscribe if you want more explorations of our cosmic context. Comment with your thoughts on what these patterns might mean. And tonight, look up at the night sky, because now you understand what you're seeing with new depth. You're looking at your galaxy, and you're looking from a location that enables that understanding. Welcome home.